Hello, hello, hello. Hopefully this is all working as it should. Oh, apart from my screen isn't. It's having a funny five. There we go. Hopefully that's going to sort itself out. But welcome, welcome, welcome. Welcome to everybody who is here waiting. Please feel free to say hi. Oh, no, I think it's showing the wrong one. Aha. That won't help, will it? There we go. Now I think it should be showing the right one. That looks slightly better. Welcome to our Sunday session. This is a A-level chemistry revision session on intermolecular forces. So welcome if you are here for the first time. Nice to have you here. If you're a regular, nice to have you back. I'm just going to flip my screen over, and it sometimes turns my camera off when I do that. So let's see what happens. Successful, nice. But welcome, nice to have people here. Hi Dylan, hi Mickey, hi Christopher. Hello Chelsea, hello BK, nice to have you here. Hi Aisha, hopefully I've said your name right. Apologies if not. Yes, it's not long now, is it? It's really not long. But this is the crunch time, right, guys? This is when it matters. This is when you need to be putting in the time, the effort, from now, not in 27 days. Oh, are you a year 12, BK? Year 12, ready for your end of year test? It's interesting, for us to know how many different people we've got. Year 12, nice. Cool. Awesome. We will get started, I think. Might as well get started. So yes, welcome back if you are new. Sorry, if you're a returner, welcome if you are new. Hello, Khadija, nice to have you here. Ah, okay, you're doing international A levels. Lovely. Well, revision is always good whenever you start. Revision is always good. And even if you do have exams this year, any revision you do now is going to be in preparation for exams next year as well anyway. So it's all worth it. Right, let's have a look and see what we're going to do today. So our objectives for this session are to understand instantaneous to induced dipole bonds and their physical properties. We're going to understand permanent dipole bonds and their physical properties, and we're going to look at hydrogen bonds and their physical properties. We're not going to look at physical properties of hydrocarbons. I think we did that last month, was it? Alkanes we did. And we're not going to look at intermolecular forces, water versus ice. That is covered in most of the specs, but we don't cover it in any of our web classes. Okay. So if you're an AQA student, then it's these spec points we're going to be looking at. If you're OCR, it's these. And EdXL, it is these. If at any point you have any questions about anything that we're going through, please feel free to pop it in the chat and I'll do my best to answer. Or if you want to answer each other's questions, again, please feel free to. When will we do spectroscopy? Oh, I've got no idea. I'm afraid I'm not in control of the timetable. You feel free to have a look and see how many timetable lessons have been put into the YouTube schedule, because that might answer your question. Or again, feel free to look back through our old web classes. We might have done spectroscopy in the past, but I'm afraid I'm not in control of that, so I have no idea. I just turn up when I'm told to teach the lessons I'm told to teach. So let's have a think about what we already know ahead of looking through our intermolecular forces revision. So first off, what is electronegativity? So at any point with any lesson, it's best if you're interactive. So if you want to get the most out of these sessions, I highly recommend that you have a go interacting. If you don't want to do it on the chat, that's absolutely fine. Just have a go at doing it in front of you, maybe write the notes in front of you or whatever. But doing is better than just sitting and absorbing. So if you would like to, can you give me a definition of electronegativity? What is electronegativity? That looks good, Christopher. The only thing I might suggest is rather than a single electron, What else could it be? So it's the power or ability, that's nice. Ability of an atom to attract. Now we can either say electron density or we can say a pair of electrons, yeah. Because a covalent bond is made up of a pair of electrons, so it's the ability to attract the pair within the covalent bond. Very good. To attract a pair or the pair, and we'll put the pair of electrons. Oh, let's try and do my handwriting. If at any point you can't read my handwriting, please do let me know, but I do try my best, even though it's appalling. A pair of electrons in a covalent bond towards itself. You don't need to say that last bit because attraction is automatically assumed to be towards yourself, but we're going to put it in anyway. A delta positive is what we use to denote a partial negative. No, it's not. A delta negative is what we use to denote a partial negative charge. A delta positive is what we use to denote a partial positive charge. Can you give me an example of where a molecule might have a dipole? What's a dipole? And so what molecules might have a dipole? Anyone know? Lovely, water's a good one. Yeah. Now, water has got a dipole across the whole molecule. It also has a dipole bond or a polar bond. So oxygen has got a delta negative and both hydrogens have got delta positive, which actually means we have a dipole across the whole molecule. Very nice. We also maybe could look at the dipole in HCl, hydrogen chloride. So we've got our very electronegative element chlorine, which is attracting the density in the bond. Excuse me. And then the hydrogen, which is quite happy to give up electron density. And that would give us a dipole across the molecule like that. Lovely. Okay, let's keep going. So, types of intermolecular force. I will do my best to use very specific keywords and to keep my key terms and keywords perfect. Apologies if I don't, but this is one of the areas where we do get quite a few people losing marks because they use terms incorrectly. So I'm going to do my best to be as perfect as I can. Okay, so instantaneous to induced dipole bonds. You may see them being described as van der Waals. You may see them being described as London forces. London forces is kind of more correct. So you either need to call it an instantaneous to induced dipole or an instantaneous dipole to induced dipole bond or an instantaneous dipole to induced dipole force, something like that. Or you need to call it a London force. So London force is specifically an instantaneous to induced dipole bond or attraction or force or whatever you want to call it. If you hear it being called van der Waals, technically van der Waals is actually a bit more of an umbrella term for a couple of different intermolecular forces, which I think is why they took it out of the spec a couple of years ago, because they realized actually they want us to be a bit more specific about which intermolecular forces we're talking about. So most of the specs should not have van der Waals in there. Are you saying induced dipole to induced dipole? Or are you saying, can I use that into that thing? I don't think, unfortunately, I think you have to write it all out, which is why it's kind of easier to just say London force. But yeah, unfortunately, I think you do have to write. If the question is, can you use the shorthand? I think you do have to write it all out, unfortunately. So how do they form? And this is why I like using the phrase instantaneous to induced dipole bond or instantaneous to induced dipole force. Describes it already, and that's the bit, especially the instantaneous bit, that's the bit that gets forgotten about. So how does it come about? How does it come about? How does it happen? Well, in a non-polar bond, electrons are in constant motion. So in what we would consider to be, I guess, normal bonds between atoms that have similar electronegativity, electrons are in constant motion, and at times they spend equal amount of time around both atoms, maybe together, maybe apart, but overall, there is no difference in charge because the electrons are spending equal amount of time around both atoms that are bonded. But perhaps every now and again, they do spend a little bit more time around one atom than the other. Not for any reason, it's just that this random motion. And in that time, we get an instantaneous dipole formed. Let's make this a bit easier. So let's say we're looking at a a carbon hydrogen bond. At some point, perhaps the electrons are spending more time around the carbon. Some point, maybe they're spending it more time around the hydrogen. At other points, maybe they're spending equal amount of time around both. And I'm going to show it kind of using like a bit of an electron cloud to show my electron density. So normally we would consider a sigma bond to have electron density between the two atoms, but of course, sometimes your electrons could be spending more time around one than the other, and that's when we get our instantaneous dipoles. So these are instantaneous dipoles form. So we've got our delta, our partial positive charge around where the electrons aren't, and then a partial negative charge around where the electrons are. This bottom one, of course, is not an instantaneous dipole because that is just a normal covalent bond. In that instant that we have an instantaneous dipole, how do we induce a dipole next door? What does this induction, how does this induction happen? We have this snapshot of time where we have an instantaneous dipole. Well, how does it induce a dipole next door? There are two ways. How does it happen? Very nice, Christopher. Yeah, exactly. That's one of the ones I find easiest to remember. Electrons repel other electrons. If I've got, let's say, my dipole shows that my electrons are spending more time around the hydrogen than around the carbon. Well, if there is a neighboring molecule, it's going to repel the electrons away from it because electron density, a negative area of negative density, is going to repel electrons, which are also negative, and that is going to induce a dipole next door. It induces a dipole. Oops. Or what? What's the other way around? How do we describe it the other way around? Good thoughts. Are the protons moving anywhere? You're right, that is kind of like the other way around, but that's not actually what's going to happen here, because the protons aren't going to move. But if we've got a delta positive next door, it can attract the electrons in a bond next door, or attract the electrons in a molecule next door, and therefore induce a dipole. Oops, that's not mean to do that. So two ways it can happen. We can get induced dipole by attraction from a delta positive to the electrons neighboring, and that induces a dipole, or we can get repulsion from a delta negative repelling electrons next door to induce a dipole next door. So two ways we can induce a dipole. So we've started with an instantaneous dipole, we then end up with an induced dipole, and we can show again if we want to, you don't have to, but we can show there's a sort of wonky electron cloud because of it. Our bonding orbitals or our bonding diagram doesn't look quite as neat when you've got a dipole. But why does this form a bond, or what some people like to call a bond or an attraction? Just going to write that down there. Nearby electrons are repelled or attracted, inducing a bond. No, inducing a dipole, sorry. Next story. How do we form a dipole bond or a dipole force or attraction? Let's say we've got our dipoles sat here. Oh, come on, why does it keep doing that? Come back. It's slow today, isn't it? That's supposed to be positive. That will help, won't it? That's positive. If we've got, oh, come back. If we've got two dipoles in neighbouring molecules, then the negative of one dipole is going to be attractive to the positive on the other. And so once you have got an induced dipole, then the dipoles can then, or the negative and positive in neighbouring dipoles can then attract one another. And that's where we get our instantaneous to induced dipole bond, or our London force, formed. So instantaneous to induced force is formed. This is what we call a London force. What? No, I'm not pressing anything. Stop. Sorry, I don't know why it flipped all the way to the end there. I wasn't clicking anything, I promise. Okay. Oh, good question. What would you expect it to be? If there's a bond angle for dipole bonds, what would you expect it to be? And actually, we have to base it off of the slightly more basic bonding model that we do at A level. But especially in this case, 180 degrees, yeah. Well, it would be because if we go the tiniest bit further from A level knowledge, some of the international A levels, I think, do one brain hybridization. And hybridized orbitals is what happens when you have bonding in a molecule. And hybridized orbitals look slightly different to normal atomic orbitals that we learn at A level across the main three examples. And hybridized orbitals, especially, I'm going to talk specifically about sigma bonding, but we know, hopefully, that sigma bonding acts along in the direction of a bond. So let's make that look better, actually. So you have, your s orbital and then your p orbital from the carbon, and they're overlapping, and that's what forms a sigma bond. Similar thing. But if you're therefore, if your electron density is going to be shifted, so let's say my electron density is shifted over to the left-hand side of my my carbon bonding orbital, so over there somewhere, then this is the empty orbital, which will be the delta positive area, and that bit will be the delta positive area that the have I done this the wrong way around? I just realised, sorry, I've got two delta negatives on the top one, so let me just change that. That would be delta. Sorry, I might have made a mistake there. Let me if that's delta negative, oh, that's supposed to be delta positive. That's why delta negative, delta positive. Oh, fine. That was fine. So actually, my electrons are in the wrong place. Oh, I have to start again. Sorry. I'm just skipped again. Go back. Try again. So if we've got, or maybe I won't draw it over my lovely diagram again. But basically, you probably would be 180 degrees because that's what a p orbital looks like, and hybridized orbitals look more like p orbitals than they do anything else. So a bonding orbital will usually look like a p orbital. Not always, to be fair, but a lot of the time, especially with the more basic molecules, when you're bonding with p orbitals, they look more like p orbitals. And so therefore you have like your bulb one side, your bulb the other side, so it will be 180 degrees. Same with hydrogen bonding, because with hydrogen bonding it needs to be 180 degrees for exactly the same reason. The lone pair usually exists within a p orbital, which is pointy, so you need to have your hydrogen in line with that p orbital, because that's where the electrons are existing. That's the shape in which you're most likely to find those electrons, so it will be approximately 180. That was a long-winded way of saying yes, 180, but you won't lose marks if you're a little bit off, because it's above A-level knowledge. There we go, bonus content there. Let's keep going though. Oh, if it'll let me. Now it doesn't want to flip over. There we go, we're back. Okay, so how do permanent dipole bonds or dipole forces form? Where do they come from? In molecules with permanent dipoles, opposite partial charges attract each other. So opposite delta positive and delta negative will attract each other. And that's kind of basically like the last step in the one we've just done. So let's not do H7 because that's nice and boring. Let's do that's delta negative, that's delta positive. I need a delta positive here. So let's do CH3Cl. When you've got a permanent dipole, a dipole that is always present because of the difference in electronegativity, then you can get your permanent dipole interacting with another permanent dipole. Difference in electronegativity causes a permanent dipole within a molecule. So when you've got a permanent dipole interacting with another permanent dipole, then you can get an interaction. One of the intermolecular forces that is held under the umbrella term for van der Waals, again, one of the reasons why we don't necessarily like to use that term anymore, is the interaction between a permanent dipole and an instantaneous dipole, a permanent dipole and an induced dipole, and an instantaneous dipole and a permanent dipole, which is basically the same thing that it was before. So all of those, I believe, come under the umbrella term of van der Waals, whereas on the previous slide, when we were just talking about instantaneous to induced dipole attractions, that is a very specific type of van der Waals force, if that makes sense. So this is our weak electrostatic attraction between opposite sides of a dipole. So this is what we call permanent to permanent dipole bonds, but we don't call it a permanent to permanent dipole bond if it happens between a very delta positive hydrogen and oxygen fluorine, and the lone pair on oxygen fluorine or nitrogen, because those we call hydrogen bonds. Again, this is where, so just coming back to what we were talking about with the bond angles, here we do need to get, they will look for 180 degrees. So try to make sure, let's do it like that. Try to make sure that your hydrogen bond, make sure that you have drawn in a lone pair on the oxygen, nitrogen, or fluorine, a delta positive hydrogen, a delta negative oxygen, and that you have got a 180 degree angle. So again, it's similar reasons. Oops. It's to do with the bonding orbitals and where they are in relation to one another, and where you have the empty bit of the bonding orbital that the lone pair can then exist in. So the electrons are spending more time around the oxygen. That means they're on the left-hand side of the bonding orbital, which means there's space on the right-hand side of the bonding orbital for your new lone pair of electrons to exist in. You don't have to be able to explain that. You definitely don't have to be able to explain that. What you need to make sure when you draw your diagrams that show hydrogen bonding is that you have a 180-degree angle. If you think you've drawn it slightly wonky, just draw the angle and write 180 so that your examiner knows it should be 180. It's just you went a bit wonky. You need lone pairs. You need to make sure you've shown the lone pair that's interacting in the hydrogen bond. You need to make sure you've shown the dipoles, any present dipoles. Oh, that's a really good question. I don't think so. No, I don't think van der Waals includes the umbrella term hydrogen bonds, because when I did my A levels, we only learnt about van der Waals and hydrogen bonds. So I think, very good question. I don't think it is included. I think van der Waals are to do with the instantaneous and induced dipoles and dipoles. So no, I don't think so, but a very good question. Don't forget, of course, that you may be asked to draw 2 hydrogen bonds, for example. So make sure, if you do, that you, like I haven't done, you plan where you're going to draw your molecules, because if I went to draw another oxygen here, I'd need to make sure I did it here so that I got the 180-degree angle. So my diagram is not very well drawn or planned there, so actually I'm going to do it here. I'm going to draw my oxygen there. If you would rather, and it's absolutely fine, draw your waters with your lone pair, your water lone pairs going off to the side like that, which is often how we draw it. That's absolutely fine. Just make sure that your lone pair is pointing at your hydrogen that you're involving your hydrogen bond in. You can't do what I've done here, which is draw a hydrogen bond like that, because technically you're saying it's not pointing at a lone pair. And one of the key aspects of a hydrogen bond is the lone pair. So if I were to draw a hydrogen bond there, I'd have to draw it coming off at the same angle as the lone pair so that I got my 180 degrees between the lone pair and the hydrogen. As it is, I'm going to do it in the same way I did the other one. No, thank you. I didn't say to do that. And draw my lone pair like that. And then my hydrogen bond there. Delta negative, delta positive, delta positive. Just put in all of the bits that you can think of when you're doing hydrogen bonds, because they want to see all of it. All of the dipoles, all of the lone pairs, everything you think might be required, they want from you. Okay, so they form between a very delta positive hydrogen and oxygen, nitrogen, or fluorine. It needs to be those guys, not because they are the most electronegative elements, but because the way they are electronegative allows them to donate a lone pair of electrons, as well as accept electron density from the hydrogen that they're bonded to. So it's important that it's just those three. Only those three are capable of forming hydrogen bonds. It basically is it is a permanent dipole to a permanent dipole. However, they are stronger. They are significantly stronger. So we have recognized that they are another level above, as it were, a permanent dipole to a permanent dipole attraction. So why are they strong? They are strong because hydrogen is small and forms a I'm going to say strongly positive, highly positive. That's the word I want. Sorry, I couldn't think of that then. Highly positive partial charge. It's still a partial charge. It's still not a full charge, but it is a strongly positive partial charge. Hydrogen is small and forms a highly positive partial charge when bonded to very electronegative elements such as oxygen, nitrogen, and fluorine. Oxygen, nitrogen, and fluorine. The hydrogen bond forms between a lone pair. And I'm going to be lazy and just put LP in your exam. Please write it out fully. It will form, between the lone pair and the delta positive hydrogen. How do we explain their strength using the difference? How do we explain their strength using the difference in electronegativity? I would expect in an exam they would ask you how it forms rather than how to explain their strength. But if they were going to ask you how to explain their strength, then you would say it's because of the greatly delta positive hydrogen. So because delta hydrogen is not very electronegative and it's bonded to a very electronegative element, it forms a highly positive partial charge, and that then forms a strong attraction, or there's a strong electronegative attraction between that very positive partial charged hydrogen and the lone pair on a neighboring atom. So I'd say something like that. Yeah. This is also a way that you could talk about how they form as well. So you may be asked to explain how a hydrogen bond forms, and you need to talk about the fact that it forms between the very delta positive hydrogen and the lone pair on the oxygen, nitrogen, or fluorine, specifically between the delta positive hydrogen and the lone pair on the other atom. Oh, do you mean how can you tell which one is going to be more strong? Which one? An example is like HF and H2O, which one requires more energy to separate? I'm afraid I'm not 100% sure what you're asking, but how would you? Yeah, well, so I mean, if it's not obvious in terms of one has got hydrogen bonds and another molecule doesn't have hydrogen bonds, so in your case, obviously they both have hydrogen bonding because they both contain a hydrogen bonded to a very electronegative element, which has a lone pair available to bond. So both of those, HF and H2O, have strong hydrogen bonding. If it's not clear which is going to have stronger hydrogen bonding, then you could talk about the difference in electronegativity and say because fluorine's more electronegative than oxygen, you'd expect the delta positive to be greater. But then because fluorine is very electronegative, it also holds on to its electrons a lot. So it doesn't necessarily let its electrons out. It does depend what it's bonding to, but it doesn't necessarily allow its lone pair to be as available. So its lone pair wouldn't necessarily be as available to hydrogen bond. So I think in an exam, you would be expected to talk about two elements which are very definitely different, but you would have to look at the energy, you'd have to use the boiling point, for example, to determine which one has stronger intermolecular forces, rather than being able to look at the structure of the molecule and then be able to determine which is which. So I think in an exam they'd make it much more obvious, if that makes sense. And I hope they implement it, otherwise they're mean. Okay, so whilst you're going through your revision, whilst you're doing anything, highly recommend that you take the chance to just think about how you're feeling, how you think your revision's going. Do you feel confident? Do you feel confident about the learning, but actually you think you might need to do some revision? It's always a good idea to kind of just keep ticking over. Quite apart from anything, it helps to support you when you're going to plan about your revision. So if you wanted to, if you can let me know how confident you're feeling, but even if it's just an opportunity for you to reflect yourself and think, actually, yeah, this is fine, or no, I'm going to need to do some more revision, or actually, all of this is getting straight over my head. There's obviously some of the core knowledge that I'm missing because I'm not understanding this. So I'm going to need to go back a few steps. So just take a second, have a think, and then we will have a go at an exam question. So hydrogen peroxide molecule can be represented by the structure shown. Hydrogen peroxide dissolves in water. Just as a note, they have given that piece of information not just for fun. Every piece of information in an exam question is put in either to give you some guidance, to give you your data to use in the question, or as like or to give you context. So here, this is guidance. Yes, it is context as well, but this is guidance. This is telling me that it dissolves in water. So in my head, I can be thinking, well, why are they giving me that information? If it dissolves in water, that must mean, because hopefully we know when something dissolves in a solvent, that substance, the solute, must interact with the solvent. When things don't dissolve is when there's no interaction. So because I've been told hydrogen peroxide does dissolve in water, I've been told that it must have a structure such that it interacts with water. Now, that can be one of two things. It's either ionic or it has got hydrogen bonding. In this case, yes, exactly. It's because it has hydrogen bonding because it's a very polar molecule, but specifically it has hydrogens that are bonded to oxygens that can form hydrogen bonds. So a really useful thing, and I know it's easier said than done, but when you're going through your exams and when you're practicing your exam questions, take a half a second, just have a look at the information they've given to you before, because I know for me, whenever I used to come across questions, I'd come across this and I'd be like, well, I haven't learned about hydrogen peroxide, so how am I meant to know how it's going to interact or what's going on? We're not supposed to know. We're not supposed to know. We've been given information so we can work it out, which is why chemistry is so hard, but why it's also awesome. So this is telling us that we can work out what the interactions happen, what interactions are happening. So hydrogen peroxide dissolves in water. State the strongest type of interaction that occurs between molecules of hydrogen peroxide and water. What do we reckon? What's the strongest type? And they've said that on purpose. They haven't asked for all different types that are possible. They've asked for the strongest type. Yeah, lovely. It has to be hydrogen bonds. It's very unlikely, although it is possible, but it's very unlikely that they're going to ask us for the strongest type of interaction that occurs between molecules of something, and it's just London forces. If they're asking a question, it's probably got a point to it. In this case, it's because they want us to recognize that it's hydrogen bonding. Draw a diagram to show how one molecule of hydrogen peroxide interacts with one molecule of water. Have a quick think about what you think that might look like. It specifically asks us to include all lone pairs and partial charges in our diagram. Good, must remember to do that then. There's actually a couple of different answers you could give, because hopefully we recognize that within hydrogen peroxide, if we look up here, we've got two oxygens, both with lone pairs, and two different delta positive hydrogens. And within water, we have got oxygen with a lone pair and two different delta positive hydrogens. Delta positive, thank you. So we could actually draw the oxygen on the hydrogen peroxide interacting with the hydrogen on the water, or we could draw a hydrogen on the water interacting with an no, that's the same one. An oxygen and hydrogen peroxide interacting with the hydrogen on water, or the hydrogen on hydrogen peroxide interacting with the oxygen on water. So a couple of different diagrams we could do here. I'm just going to do, because it's slightly easier to do. Oh, I haven't given myself enough space. Never mind. I'm going to do that one. And look, they've given us the structure of hydrogen peroxide, so we don't even need to know what the structure is because they've told it to us. Just need to make sure that I include all lone pairs and partial charges. Now, they're probably not going to penalise you if you forget one of the ones that's not involved in the hydrogen bond. But if they've asked for all of them, let's just not risk it. Let's just put all of them in so that there's absolutely no way that they can get cross with us. Notice that my hydrogen bond is a 180 degrees between the hydrogen and the lone pair. along the line of the hydrogen bond, oxygen-hydrogen bond. And I think, I'm just double checking, I've put in all of my lone pairs and ultra pluses. If you want to, you can put in 2 pairs of lone pairs on each oxygen. But actually at that point, you're going to get a little bit crowded and they're not worried. This is the lone pair that they're interested in. That one. But if you wanted to put in your other lone pairs so that you've got 2 pairs of lone pairs on each oxygen, that's absolutely fine. Okay, I think that's all I wanted to say. Let's keep going. What about properties then? We've kind of already touched on it, so hopefully this will be nice and easy. So properties of simple molecules, i.e. simple covalent molecules. The physical properties of small simple molecules such as carbon dioxide, water, methane, etc. depend on the intermolecular forces between them. Hopefully this makes sense. As you increase your electrostatic attraction strength, what is going to happen to your melting and boiling point, do we think? As you increase your electrostatic attraction strength, i.e. we go from instantaneous to induced dipole forces to permanent Notice we've missed out any of the other wishy-washy ones in the middle because we don't really learn about them at A level. Permanent to permanent dipole forces to hydrogen bond. What's going to happen to the boiling point and melting point and why? We reckon they're going to increase. Why? Boiling point and melting point increase yeah, lovely. More energy. So because, oops, let's try and write that again. Got the writing. Because more energy is required to overcome the attraction. As it gets stronger, attraction? No, attraction. As the electrostatic strength increases, as you get between the different bonds, you're going to get more, or going to need more energy to overcome the attraction. Also, just as kind of like a little bit of an extra insight, the more instantaneous to induced dipole forces you have, the greater the boiling point or melting point is going to be. Let's put increasing numbers of instantaneous / strength of instantaneous induced dipole forces, increasing numbers of / the strength of. Oh, that is not a word. Strength of, and again, increasing numbers of hydrogen bonds. So, i.e., the more instantaneous to induced dipole forces you have, i.e. on longer chain molecules, the more opportunities you've got for these instantaneous to induced dipole forces to appear, the higher the boiling point is going to be. If you've got more permanent dipole attractions happening between molecules because you've got more permanent dipoles within a molecule, then you're going to get a higher boiling point. If you've got a molecule that can have more hydrogen bonds, then you're going to get a higher boiling point or melting point. So as well as being able to compare between the three, we should also be able to compare within each type of intermolecular force about what happens when you increase the number or the strength of the instantaneous the intermolecular force, sorry. Particularly, that's the one that we kind of focus on, is the in between the instantaneous to induced dipole forces, because we look at it with halogens. Why the halogens have different states at room temperature. Why does it go from gas to liquid to solid when you go from chlorine to bromine to iodine, for example? And it's because the size of the instantaneous to induced dipole force is greater because you've got more electrons. So also need to be able to compare within the specific intermolecular attraction as well. Nice. Okay, let's keep going. Final bit of info here. Solubility. The solubility of small simple molecules depends on the polarity of the solvent and the solute. We've already touched on this. But polar molecules dissolve well in what type of solvent? And can you give me an example? Polar molecules dissolve well in what type of solvent? And can we have an example? What type of solvents? Yeah, lovely. Polar and polar. And again, it's because they can interact. If you've got a dipole, it can interact with a dipole and water. If you don't have a dipole, then it can't interact with the dipole and water because it's got nothing for water to interact. For example, water is a lovely, easy polar molecule, etc. What about non-polar? What type of solvents? What type of solvents dissolve non-polar molecules? And again, do we have an example? Depending on the alcohol, I might actually discuss, depending on how long the chain of alcohol is. If it's really long, I guess you'd call it a non-polar solvent. But you could probably call some alcohols polar solvents. They're a bit annoyingly in the middle. Technically, you've got the OH, which has got a dipole in it, so you could class it as a polar molecule. The longer the chain is, though, the less of a dipole you've got across the molecule. So it gets a little bit annoying. But yes, it is non-polar. Very good. Non-polar. Yeah, like cyclohexene. Yeah. Or cyclohexane. Yeah, both of those. Yeah. I don't think you would call cyclohexene a polar molecule because although it has got an area of slightly higher electron density, there's not a dipole across the molecule. There's not a split charge. So dipole, two poles, the split charge is what you're looking for when you talk about whether or not something is polar, whether a molecule is polar or not. Has it got a split charge across the molecule? But yes, cyclohexene, benzene, carbon, methane, tetrachloromethane, even, let's get it right around, tetrachloromethane. So even though, and this is just an important aside before we move on, even though carbon-chlorine bonds are polar, they have dipoles, the molecule itself is not polar. Think about why that is. We've got a lovely tetrahedral shaped tetrachloromethane. Each one of those bonds is polar or has a dipole, but the molecule itself is not polar because it's symmetrical and because the dipoles cancel. Oh, I don't think I know what chickene is, I'm afraid. Not heard of that before. Let's finish up then. What kind of intermolecular forces are involved in the solvation of polar molecules? I.e., what intermolecular forces are going to be present when you try to dissolve something polar in water? Are going to be present. Anybody know? When you've got, for example, water or something dissolving in water, what intermolecular forces will be present between the molecules? Definitely. Permanent dipole. Solvation, good question, very good question, sorry, well done. Solvation means the dissolving of. So what kind of intermolecular forces are involved in the dissolving of polar molecules? When you get to year 13, most examples they kind of add to Hess cycles by talking about solubility and solvation. So yes, sorry, I should have clarified. That is something dissolving. So yes, definitely. There's definitely going to be permanent to permanent. Permanent dipoles. Sorry, dipole forces. We're going to get our induced ones, so our London forces for instantaneous to induced. Instantaneous E-us to induced dipole forces. Can't be bothered to write it out, so I'm being lazy. Correct. And if it is dissolving in a polar solvent, what are you going to be very very likely to see? Probably also going to see some hydrogen bonds. I'm going to be lazy and just put H bonds. I can't, off the top of my head, think of an example when you don't see hydrogen bonding between them, because you've got an oxygen and a hydrogen in the water. So all you need is another electronegative element connected to a hydrogen in the other molecule. Excuse me. So I can't think of an example when you wouldn't see it, but I'm going to put probably hydrogen bonds, because obviously just take it molecule dependent. What kind of intermolecular forces are involved in the solvation of non-polar molecules? This is a little bit easier. If it's non-polar, i.e. there aren't any dipoles, then it must be what? Only, yeah, lovely. Only London forces are in instantaneous to induced dipole. Very good. Because there's nothing else possible. Well, very unlikely. I'm not going to say never, but very unlikely that anything else is possible. If it's a non-polar molecule, then you're not going to get anything else happening. Okay, let's finish up with an exam question. So just take a second. How did you feel about that? Are you happy? Are you not happy? Etc. And then we've got some nasty exam questions to finish up with. So, this links back to, I can't remember who it was that asked the question, but let's have a go at this exam question. Explain, in terms of electronegativity, why the boiling point of H2S2 is lower than H2O2. So that's what I mean when I said you'd need a little bit of extra information. So here they've told us that the boiling point of H2S2 is lower than H2O2. So now we've got to work out why, or to explain why. Anybody got any thoughts? Yes, really nice. Good. Well done, Christopher. Well done, Surat as well. Very good. So why is that? Why is there no hydrogen bonding in H2S2? There's no hydrogen bonding between molecules of H2S2. Why? Whereas there is between molecules of H2O2, hydrogen peroxide. Yes, so good thought. There is a lone pair on sulfur. Sulfur's in the same group as oxygen, so behaves very similarly to oxygen. That's why we get things called thiols, which you may or may not have heard about, which is like SH instead of OH, so a normal alcohol. is an OH, a thiol is an SH. So they behave very similarly. They have lots of similar things. So and so sulfur does have two lone pairs of electrons. So good thought. It's not about the sulfur's lone pairs as such, but yeah, you're right that hydrogen bonding has to occur between molecules that contain an oxygen, a nitrogen, or a fluorine that is bonded to hydrogen. Good. So it must be to do with the difference in electronegativity between oxygen and sulfur. We can't get although we might have a permanent dipole, we don't get the split of the electronegativity. No, that doesn't make sense. We don't get the, how to phrase, come on, brain. You get a greater, thank you, brain. There's a greater difference in electronegativity between hydrogen and oxygen than there is between hydrogen and sulfur. So you get a stronger dipole formed or a greater dipole formed, a bigger split, and therefore you can get hydrogen bonding with H2O2, not with H2S2. So let's explain. There's no hydrogen bonding between molecules of H2S2, whereas there is between molecules of H2, because there is a greater difference in electronegativity my handwriting's appalling, apologies, between hydrogen and oxygen than there is between hydrogen and sulfur. So notice that my explanation went on to talk about why we get hydrogen bonding, not just that there is a difference in electronegativity between oxygen and sulfur. The key is their interaction with the hydrogen that causes the hydrogen bonding. So notice I didn't just say oxygen is more electronegative than sulfur, because that's not enough of an explanation. That's too surface level. We need to go down another layer and say, therefore, the electronegativity difference between hydrogen and sulfur is not great enough, or there is a greater difference present in hydrogen peroxide between hydrogen and oxygen. Okay, final thing then, final minute. Which of these substances does not show hydrogen bonding? Take a second. A, B, C, or D? From first glance, it looks like they all should. Now, they wouldn't be asking this question if they didn't, if there wasn't an actual answer. So just have a look. What do we reckon? A, B, C, or D? And if you think you know the answer, why? Why is that the answer? If you want to, get rid of answers that you know are correct. So it's a usual exam technique when you've got multiple choice questions. There should be at least one, if not two, that are obviously incorrect because you know, for whatever reason, it can't be that answer. So you can usually get rid of those, and then it's just a case of guessing between the other ones. Or you can work it out, even better. Yeah, good. Well done. It is D. Correct. Lovely. And it's exactly right. They've put it like that specifically to be annoying because they want you to kind of be confused by it. They want you to notice that there's a hydrogen and a fluorine and think, oh, but it must be okay. That must be hydrogen bonding. But no, you're absolutely right. Actually, the structure of the bonding is that we have the fluorines are bonded directly to the carbon, not to the hydrogen. So there's no hydrogen that's covalently bonded to an oxygen, a nitrogen, or a fluorine. Oh, that's not gone well. No, it's not letting me write there. No hydrogens directly bonded to oxygen, nitrogen, or fluorine. Whereas there is in all the other ones. So they can show hydrogen bonding. Nice one. Well done. Okay. So we've looked at instantaneous to induced dipole bonds and their physical properties. We looked at permanent dipole bonds and their physical properties. And we've looked at hydrogen bonds and their physical properties. Anybody? Oh, that is trifluoromethane. Yeah, nice. Well done. Does anyone have any questions before we disappear? If not, have a lovely rest of your end of your weekend. Good luck to those of you that are doing exams and stuff. I may or may not see you before your next exam, so keep an eye out for when we've got classes coming up and all that sort of thing. And I will, yeah, wish you all the best. Good luck with revision, and then good luck with exams if you've got them. And I will see you soon. Thank you very much, guys. Well done. Oh, I don't know when the next one is, but feel like have a look on the what's it called? I think they've got some scheduled, so have a look at the schedule. Okay, thank you. Bye.